Thanks, everyone. I'm Vyas. I'm a senior software engineer at NVIDIA, and today I'm hoping to tell you exactly as much as you need to know about GPUs and not too much more. So GPUs, I think, for a lot of people are thought of as kind of a daunting concept, and I'm here to kind of try and convince you that, in fact, most of what you really need to know, you already are kind of familiar with those concepts from just pure Python code. So to start with, we're just going to look at, in fact, for most of this talk, this really, really basic example of Python code, just adding together two lists of numbers, okay? The mental model we're going to work with is that you've written your code. It goes through some sort of translation process, right? There's some code running that translates your code and gets it down to what the hardware executes. And then you have the low-level hardware execution, in this case, potentially a CPU, potentially a GPU. Now, in Python, that translation process is all done by the CPython interpreter, right? And we know that that can be slow. One of the ways that people are used to overcoming this is with precompiled libraries. So NumPy is the standard way people do this kind of addition operation, right? You make your arrays, and then you tell NumPy to do the work for you. And NumPy kind of elides all of this translation cost by precompiling a library for you, which means that at runtime, most of the work that you have to do to translate is already done. And every time you execute, you're going straight down to the CPU. In addition to eliding that translation overhead, the pre-compilation also means that you get a lot of other optimizations for free. And those optimizations are going to be critical to what we talk about today, because a lot of those are similar to the types of optimizations that you also need to get in your GPU code. Hopefully, if you're here and interested in GPUs, you've all heard of CuPy, which is NumPy on the GPU, right? It lets you run the exact same code and hopefully get GPU acceleration. Now, the story with CuPy in terms of that translation process is a little bit more complex. With CuPy, because you have code that both runs on the CPU, all the stuff that launches GPU work, and the GPU code, compilation is a more complicated process. And at runtime, your process is also more complex because you have to orchestrate the work that's being done both on the CPU and the GPU, and you have to orchestrate things like memory transfers. So working with this model today, let's start at the very top and try to understand what sorts of translation overhead you might first encounter if you're working with GPU code. So with NumPy, we talked about compilation, and I mentioned that the story is a little bit more complicated for CuPy. One of the main reasons that it's complicated is because while you can compile a single NumPy binary that runs on, say, a particular CPU architecture, you may be expecting to take you might expect the same thing to happen with CuPy, right? You get one binary and just run it regardless of what GPU you have. But of course, it's never that simple. You need the same sort of extra access to account for the different GPU architectures that you need to be able to run on. Now, GPU architectures are also versioned. I've put some of the examples up here. And as a user, you might expect that by installing a binary, if you switch out your GPU, it would still work. As a developer, you might want to build a single binary and have it work for a wide range of GPUs. In order to make that a reality, the way that most GPU code works is by pushing some of that translation cost, that compilation cost, to runtime. Many of you hopefully have used libraries like Numba, JAX, Torch, all of which involve some form of just-in-time compilation, JIT compilation. The key here is that while in most of those libraries, that process is explicit, something that you write in your Python code, with most GPU libraries, JIT compilation is implicitly always part of the process. It's not something that you can avoid, because it's necessary at runtime to adapt the code to run on the GPU that you observe. So one of my goals here today is to sort of give you little tidbits of advice on how you can overcome some surprising slowdowns or unexpected behaviors when running with GPU code. Here's one of the first things, right? You start running your CUDA kernel, and all of a sudden, everything seems to freeze up. And the reason is because of this JIT compilation. So what can you do about this? Well, the first time you're running, not much, right? You need that code to compile. It has to run on your machine. But what you can do is ensure that everything that is JIT compiled is going to stay cached and is going to keep running the next time without having to compile it over and over. Now, I've put a couple of examples of ways that you can, of environment variables that certain things support. So this is, CUDA's own compilation cache. This is Jax's. Jax actually, as far as I know, doesn't cache by default. You have to ask it to. But the same sort of thing exists in almost every major library that runs GPU kernels. CuPy has it, Torch has it, TensorFlow has it. And so making sure that you cache these, particularly in cases where you're in ephemeral environments, say like Docker containers, can help you reduce the end-to-end workflow time for almost everything that you do. Because rather than paying this JIT compilation cost every time you run, you just pay it the first time, and then you're done. All right, so if compilation is the entry point to this translation step, what happens next? Well, in Python, I actually kind of lied a little bit in this figure, right? We have this conveyor belt of items that you're churning through, which means that you're not just calling down once to the CPU lower level code, you're calling once for every single pair A and B. Now, with NumPy, one of the major benefits is that you get rid of those, right? All of those calls happen at the low level in the C code that's been precompiled. So how big of a difference does this actually make? I timed this on my machine. It's going to be slightly different for everybody. But order of magnitude, these Python calls are taking about 30 nanoseconds for me, while the NumPy pure C functions take about 1 nanosecond. This is just the pure function call overhead, right? Not doing any particular work. This is a pretty big gap, right? And this is why people like extension modules in Python, the ability to compile these low-level libraries. Now, we're here to talk about GPUs. So how does this translate to something like CuPy? Well, with CuPy, you have, in some ways, an even more challenging problem. What you're trying to do is make a function call that's going to cross not just software boundaries, but hardware boundaries, right? You're going from the CPU to the GPU. And as a result, this thing actually turns out to be even more expensive. In fact, we're talking about 3 orders of magnitude. It's a few thousand times slower to run a CUDA kernel, that's what a GPU function is called, than it is to run a nice little C function. So what does this mean for you? If you are writing code with CuPy or any library like it, every single time that you execute something like this, A plus B, you're paying this cost. So how can you get rid of that? One of the most powerful tools you have available to you is kernel fusion. Kernel fusion is the idea that if you have a sequence of functions that all are performing these types of operations, things that are pointwise are often best for this, but really there's a lot that you can fuse. Instead of calling them as separate functions, you again JIT compile and you produce one kernel, one big function that does all of the work. CuPy supports this, Torch supports this, Jax supports this. Most of the major GPU libraries have some mechanism for this. Using this kind of JIT compilation, you can pay, again, a one-time cost where you precompile these large things. And again, remember, making sure your caches persist is a big part of this. Once you've JIT compiled your code, future executions don't pay that cost ever again, so everything can go faster. So that's tool number 1. The second tool that you have for making some of this a little bit cheaper is to hide that kernel launch latency. So to understand what that actually means, throwing a little bit of latency and kernel launches, what exactly do I mean by that? We need to understand a little bit more about how GPU execution actually works. The most important thing that you have to understand about GPU execution is that it's asynchronous. Think of it sort of like dropping off mail in the mailbox, right? If I'm trying to do some GPU work, maybe I do a bit of prep on the CPU, and then I launch my kernel. Once it's been launched, I've dropped the mail in the mailbox, and then I can go along and start doing the rest of my work. Meanwhile, the GPU comes back, picks up your mail, and starts working on it. These two things are happening completely in parallel, which also means that as soon as you've launched the kernel and you can do and you're doing other CPU work, one of the many other things you could do is launch yet another kernel. So this is a key to being able to hide kernel launch latency, is to make sure that you're doing all of this work on the CPU while the GPU is busy. Typically for the workloads that are GPU heavy, the GPU is the workhorse, right? You can't afford to waste cycles on the GPU, and so making sure that your CPU orchestrator is doing its work while the GPU is busy is critical. Another major point to be aware of is the fact that here I'm just showing this example with one work stream, right? All these kernels are running on the GPU in sequence. GPUs also support, in fact, multiple parallel work streams. So what you can do, in fact, is have a single CPU orchestrating multiple parallel work streams on the GPU to maximize the throughput of what the GPU can do. Now, at some point, most likely, you're going to have work that needs to come back to the CPU, right? And these are what we call sync points. When you sync the GPU device, at that point, everything on the CPU stops and waits until everything you've submitted is completed. That kind of process, while necessary, is expensive, right? So one of the first things to be aware of when you're working with this kind of workflow is don't sync any more than you have to, because synchronization is expensive. Make sure that the CPU is being kept busy is another big part of this, right? While the GPU is churning along, if you can do work on the CPU, you want to keep that working as well, because in order to get the maximum efficiency out of your system, you really want to be using both the CPU and GPU processors the entire time, prioritizing the GPU in the sense that if you need to schedule GPU work, the CPU should be doing that first, but afterwards, doing extra work on the CPU. Now, so far, everything I've said is focusing on the processing side of this. What's actually happening in this early prep step is typically memory operations, right? You're copying data over from the CPU into the GPU, or preparing the arguments that you have to send over, things like that. And now we're getting into the memory side of this, which is another crucial part of the puzzle. When you're working with CPUs have complex memory hierarchies, right? There's various caches that bring data up from your main memory up to the registers where the core work happens. But an important point with how CPUs work is that a lot of the handling of pulling data up this hierarchy is implicit. It's done behind the scenes for you, and especially if you're writing compiled code in something like C or Fortran or whatnot, that code is going to be the underlying code that's being generated is going to be generated by a compiler that's trying to make good decisions for you. So a lot of the decisions about how memory is translated up and down the stack is done automatically for you behind the scenes. You can write code, if you're aware of this, in certain patterns in order to facilitate better data movement, right? And that's something we'll come back to in a second. But ultimately, data is being read up in these little chunks. They're called cache lines, from lower levels to higher levels of the hierarchy. And your best bet is to try and make as much use of data locality as possible. On the GPU, the core transfers that have to happen are explicit, excuse me. You are responsible for telling the GPU when you want to move data from the CPU over to the GPU. And a lot of the special memory spaces that exist on the GPU, things like shared memory, constant memory, are up to you to manage. Now, that's not to say there's no way to get automatic memory migration. Tools do exist, but in practice, very often you do want to do this manual migration yourself. And the reason is twofold. First is that the deltas in the performance between these different steps in the memory hierarchy are huge. And so if automatic decisions are made that are suboptimal, the performance penalty that you pay is very large. And the second thing is that GPUs in general don't have nearly as much mechanisms built in to hide latency from you. CPUs do a lot of work to hide latency, something we'll talk about in a second. And as a result, you get a lot of really good performance. Even if you don't necessarily write the best code, you'll get decent performance because the CPU is trying to protect you, at least relative to a GPU, where a GPU gives you no protection against this. And we'll talk about why in a minute. So in practice, what does this mean for you? For most of you who are probably not writing kernels on a regular basis, on the last slide, I talked about keeping the CPU busy and the GPU busy, right? Making sure everything is co-processing. The next step here is also making sure that you keep all of your memory transfers, all your memory spaces busy. If you need to be transferring memory from the CPU to the GPU, and you need to be doing compute on the CPU, and you need to be doing compute on the GPU, you need to be thinking about how long each of these tasks take so that you can schedule them appropriately. And a lot of this comes in for AI when you're thinking about your data loader pipelines, for instance, right? How do you ensure that you're writing good data loader pipelines? You want to make sure that all of these different memory transfers are happening at the right times. For those of you who do write some level of kernels, for instance, if you're using things like torch.compile or jax.compile, if any of you use numbacuda, in those cases, it's also important to be aware of these special memory spaces on the GPU, things like shared memory or constant memory. Being able to load data into these really fast little caches and leverage them can give you huge speedups, right? But that's where it really comes into more of the kernel authoring side of things. So I promised a little bit more of an explanation of latency and why it matters. And for that, I'm going to jump to a very different example. This is a rough map of my commute from home to work. I just picked a park close to me, and this is up in the Bay Area. So, on a good day, this is an hour's drive. On a bad day, it goes up to an hour 45. That's life. But even on those worst days, the worst case scenario for this, say an hour 45, is still probably the fastest way to get from my home to the office. In that sense, the choice to drive is a latency minimizing choice. Now, latency is effectively, in this case, just how long it took me to get from point A to point B. And there's a lot of factors in that, right? Distance being the obvious one, but also traffic. What are the obstacles in the way? Now, instead of making the latency minimizing choice, I could instead make the high throughput choice, which is to go take the train, right? Now, taking a train, in this case, will pretty much always be slower for me. Well, taking all sorts of public transit. There's some walking and busing in there, too. But the advantage of public transit is that a train or a bus can take a much larger number of people, right? And you could schedule those trains such that they're carrying a much larger total number of people along the pipe from home to work. The fundamental thing to understand about GPUs is that GPUs, instead of doing what CPUs do, which is minimize their latency, they try and maximize throughput. It's not about how quickly can I get this one result, it's about how quickly can I get tons and tons of results through. To understand this a little bit more, let's talk about one of the other core optimizations that CPUs often make for you, or CPU compilers will make for you, if you write your code correctly. I mentioned earlier that sometimes if you write your code correctly, CPUs will allow you to process a couple of data elements at once, right? This is called vectorization. Here's a pretty trivial example of how if you're loading in adjacent memory elements and you're doing the same sort of mathematical operation, for instance, the CPU compiler will know that this thing can be done with what's called a vector instruction, which means that it's going to operate on both of these data elements in parallel with a single instruction. Sounds great, and it's faster. The problem is that if you write code that is not amenable to vectorization, which basically means in this instance, this code that's very branched and doing different things, the compiler will decide, okay, well, this is not something I can vectorize for you. Now that has a couple of different costs, right? I mentioned earlier talking about how memory is funneled up through the cache. That means that perhaps you're going to get lower cache efficiency if you're not using all the memory in a chunk that comes up. It also means that you're going to get worse runtime performance because you have to run 2 instructions to do this operation rather than 1. I also told you that CPUs are designed to minimize your latency. And a lot of what CPUs do, and what compilers really do, is find ways to make this this kind of branching code look as fast as possible, right? Some of you may have heard terms like, branch prediction, right, or prefetching. They can pull in data that they think you might need. They can do extra computations of results that they might throw away, all to make it so that the real result that you need happens. But all of that is expensive, both in terms of hardware and in terms of total cycles. GPUs don't really do any of that. There's very, very little special hardware in a GPU to handle this kind of stuff for you. And as a result, most of this decision around branching and what data goes through what part of the pipe is made at runtime. Branching code is very expensive. In fact, it's orders of magnitude more expensive to branch on a GPU than a CPU, in particular because none of this is going to be prefetched for you, and because the number of parallel units that's operating is extremely high. And so writing code like this that is unfavorable for a GPU is going to cost you much more. I mentioned parallelism. Parallelism is a huge part of what makes GPUs do what they do, and it's also critical to understanding this high throughput. So let's pause for a second and think about that. If you're here for the practical advice, I gave you a couple bits later. I'll give you a couple more in a second. But if you're here to understand like why GPUs are important, what they do differently from CPUs, this slide is sort of the key thing. Now, the numbers that I've put up here are illustrative. I haven't picked a particular CPU or GPU hardware, but they're in the ballpark for a lot of the modern architectures that you see. So a typical CPU has, say, 100 gigs a second of memory bandwidth, right? That's how fast memory is going to go from your DRAM to your chip to compute. And the latency, the amount of time it takes for that to happen, is, say, 100 nanoseconds. For a typical GPU today, you're looking at much larger memory bandwidths, something on the order of 5 terabytes a second. I think the Blackwell chip is 8 terabytes. It peaks out at 8 terabytes a second. And you're also looking at much higher latencies. Like I said, it's going to take longer for that data to get to your chip. So this number at the bottom, bytes per latency, is just multiplying these two together, right? In that amount of time it took to get data from point A to point B, what is the total amount of data that can actually make it there? And you see that this gap is pretty huge, right? GPUs are giving you 2 million bytes, and a CPU is giving you like 10,000 bytes. All right, you're getting all this data. What do you want to do with it? Let's say you're doing DAXP. This is a pretty standard operation. Just take a constant, multiply it by a number, and add it to another number, right? And we're doing DAXP, so they're doubles. So each of these is 8 bytes. That means you're using 16 bytes for an operation. Well, if I'm bringing in 10,000 bytes to the CPU and I'm doing 1 DAXP, that means I'm only using 16 of 10,000 bytes. That's kind of wasteful, right? All this data is coming in, you're not doing much with it. On the GPU, it's way worse. You're using like 1/millionth of the data that's coming in. So what can we do about this? This is the reason why GPUs care about parallelism. On a CPU, say you've got a few hundred threads, right? Like a Threadripper has around 196, I think. Then you can improve your utilization of all that memory quite a bit. You can use about a third of it. But GPUs have hundreds of thousands of threads. Again, I think a Blackwell has 312,000 or something. So if that's the maximum hardware limit, all of a sudden you can see why that high throughput choice matters. You can funnel huge amounts of data to your GPU and then just feed it to huge amounts of threads to compute on all of this in parallel. So instead of just doing 1 DAXP at once, or even 200, you can do 300,000 of these, right? So if you take nothing else away from my talk, take away this slide. This is the core of what makes GPUs do what they do today, and all of the architectural decisions that are made based on this kind of computation. Now, I've talked about some of the costs of that parallelism, right? You have to be more careful about how you manage your memory. You have to make sure that you're utilizing your CPU and your GPU at the same time. One of the other major costs that many people in this, especially in the AI space, find confusing is the fact that you get different results sometimes when you run the exact same code. So why does that happen? Well, I'm sorry to tell you that it actually is less to do with GPUs and more to do with parallel computing in general. So here I'm showing you an example of a simple tree reduction given these 8 numbers, 0.1 to 0.8. If I add them together in sequence, you expect to get 3.6. Great. Unfortunately, if I do this in parallel and I happen to use different orderings, I could wind up with different numbers. I reproduced, not exactly with these numbers, but I can reproduce this on my machine right now using a Python thread pool. You don't even need real parallelism, right? You don't need free-threaded Python. with even a thread pool, you can reproduce this with a sequence of 10 numbers today. And the reason for this is the fact that numbers on a CPU or a GPU, anything, are represented in binary. They're represented with floating point. And as soon as you have fractions, and you're using floating point, those numerical representations are inexact in some sense, and the operations you perform are inexact. So floating point arithmetic in particular is non-associative. The order in which you do these operations can change the result. So what can you do about this? Well, there's two different answers to that. When you're building up your models, when you're building things up for the first time, this kind of thing can trap you, and it can trick you into thinking you're doing something wrong. And during those prototyping phases, it's really useful to get the same results. So for those times, what you can do is turn on determinism, which a lot of libraries today do expose. I've given a couple of examples here. For Torch and TensorFlow, there are ways to tell them to give you deterministic answers. The major caution with this is that this determinism only exists on your exact machine at that time. If you upgrade your software, or if you switch to a different CPU, a different GPU, those results still can change. This is just to give you run-to-run determinism. So the first takeaway here is, while you are prototyping, while you're trying to sort this out, it's useful to turn these kinds of things on. But know that A, there's limits to how deterministic you can truly make that, and B, do not expect that this equivalent, the exact equivalence to persist once you've switched over to different hardware. All right. So I've hopefully walked through a few of the different and very common ways in which I've observed people getting confused by the ways that GPUs work, the ways that GPUs are different from CPUs. I had sort of two goals today. One was to give you sort of a high-level view of the architectural choices that make a GPU different and useful. And then for those of you who are actively working on this kind of code, trying to give you a few of the different ways in which you can mitigate some of the unexpected costs or differences between CPUs and GPUs. We talked through JIT compilation, kernel launches, the memory transfers, and floating point error. So hopefully, with all of this armed with some of these tools, you're a little bit more equipped now to make some decisions about how to use your GPUs best. And with that, I'll say thank you, and I'll take any questions.
Thank you so much. You had mentioned a few slides back on, like, you had showed the different ways to do the computation. You had the branching logic of, like, it was like the modulo divide on, like, whether or not to use multiplication or division.
Oh, you're talking about this?
Yeah, this one right here. Is there like is there a way that you would have to, like, would you chuck this at like Torch or something like that to help make this more optimal for GPUs, or is there something that you can do in your design of like your CUDA kernel to make that better beforehand, or is there work that the CPU can do to make this so that you're using the more optimal, I forgot the vector function that you'd mentioned?
Yeah, I may have been a little confusing, but so there's two things. The vector instructions are more of a CPU thing, but the thing that you really want to do is ensure that on the GPU, if you have data, you want to, and you're writing a CUDA kernel, so at the low level, if you're writing a CUDA kernel, you want to avoid branches in your code as much as possible. And so one way you can do that with pre-work on the CPU is to, sort your data in certain ways, to chunk your data in certain ways, to ensure that when you run the kernel, all of the blocks of data that are operating on always go down the same code path. If you're worried about the CPU side of it, then you want to write code that your CPU, your compiler can vectorize, which means, again, that is more about the way you write your code, whereas the way it is on the GPU is more about how you structure your data. It's often possible to replace branching code by using like some tricks of mathematics, right? Like you want to pre-calculate some prefactor once and then you apply it to everything. So those are other ways that you can minimize the branching, basically.
Cool. Thank you.
Hey, I was wondering, you mentioned earlier about you're trying to like saturate your CPU and GPU with computation.
Yep.
And running like multiple kernels in parallel.
Yeah.
or kicking off multiple kernels while the CPU is doing its own thing.
Yeah.
When you're writing multiple kernels and running them in asynchronously, do you try to think about how the resources are going to be utilized, or like trying to optimize how the kernels are using the resources in order to like optimize how well it's running?
Yes, that does matter. So if you are free to queue up kernels however you want, and when the GPU scheduler sees that you've queued up kernels, it's going to decide whether or not it can actually afford to schedule them at the same time. So if you schedule 2 kernels that are both going to like use up the entire GPU, for instance, then it's not going to work. When you run the kernel, you specify like how many threads and how many blocks that you get, right? Which is the units of parallelism. So if you're writing your code and you're trying to schedule multiple concurrent kernels, you do basically want to do some math ahead of time to say like, okay, this GPU supports this much concurrency. How much of that like thread do I want to allocate to this kernel versus this kernel?
Could you then use that to like decide how many machine learning models you want to train at once and how much resources you want to give to each one? Or like, how do you do the math ahead of time by hand, for example, or do you use programs to kind of calculate it for you?
Depending on the level of abstraction that you're working at, the answer is sometimes you can use tools ahead of time. I typically would not recommend training multiple full machine learning models at the same time, because typically you're going to be using enough data to saturate the GPU. On the other hand, if say you're using like torch.compile to put together your model, in that case you can envision that like, some of your data preprocessing steps, for instance, or in your data loader that's ongoing, or you could be putting in certain layers that only need to process like a subset of data. In those cases, you would probably do a little bit of math in your model to figure out how much to launch on each one.
Thank you.
Thanks for the presentation. I'm curious if you can speak to differences or how much this applies for unified memory, like the DGX Spark. Are there things that, if you can speak to that, I guess,
Yeah, sure. That's a great question. I should also check you on terminology, because there's actually a couple things that we talk about with unified memory, right? One of them is this automatic memory migration that's existed for a long time between CPU and the GPU. And that's like a convenient tool that you can use to make it so that the memory spaces are the same, and then you pay a little cost for the automatic migration. What I think you're asking about is specifically the newer hardware, where the CPU and the GPU are on the same chip, right? And with those systems, the numbers change, and so the hard thing with GPUs is often you're aiming for peak performance, which means you have to benchmark. But the reality with the new systems is that it's much cheaper. So like in those early slides where I was trying to point out that this PCIe bus, this is no longer accurate, right? They're much closer together. So you get a lot better performance out of that. I think I guess the challenging answer to your question is you have to benchmark it for a particular application. But it can make a lot of this faster.
Thank you very much, Vyas.
Yeah.